Okay, I'm going to talk about intermolecular forces today. And I want to explain to you the difference between intermolecular forces and intramolecular forces. We've been talking strictly about the stuff that holds a molecule together. I'm going to now talk about stuff, the attractive force between molecules. That's the big difference for this, okay? Intermolecular forces or van der Waals forces are the attraction between molecules, not within a molecule. So, the covalent bond, the ionic bond, even the metallic bond you could think of as holding guys together, holding two or more atoms together. What I'm talking about with intermolecular forces are the attractive forces between water molecules or hydrogen molecules. Okay? And there is a big difference. They happen to be very important for several reasons. Very important in particular what the guy looks like. Is he a solid, a liquid, or a gas? All of that's going to be determined by how strong the intermolecular forces are. All right? So this helps to determine, it's not the only factor, but it helps to determine, in part, the phase of the substance. And if you look on page 309 and 310, some of the same pictures I'm going to show you here will be on those pages if you needed to see them again. Because I'm going to show you several pictures. I have two demos to show you today, kind of neat ones. And then we have a lab, which I'm not sure if I'm going to do today or possibly tomorrow. I forgot that I have stuff set up back there for Chem 2, and we'll see how much time we have. We probably could do it. Okay, either way. Intermolecular forces determine the phases. How could that work? What do I mean by that? Okay. Well, here's what I mean. If you expect things to be held together really well, what phase do you think they'd probably be in? Yeah. And things that are not held together very well would probably be a gas, and things in between would be a liquid. I could turn something from a solid to a liquid to a gas by doing what to it? Heating it. I could heat it, but that's because if I heat it enough, I start to break those intermolecular bonds. Okay? I don't break very easily the bonds that hold, for example, water to H's and O's in water. Here's your O. Yeah. Here's an H. Here's an H, right? The bond that holds the O and the H does not break when you boil water and turn it from a liquid to a gas. Okay? Or when you melt ice and turn it from a solid to a liquid. So what we're talking about is the attractive force between molecules. So if I've got an H here and an H there, remember what happens. One side of these molecules are going to be slightly, remember the arrows I had you draw? Right? One side is going to be slightly negative. What's that mean? The other side is going to be slightly positive, right? So the attractive force between molecules is what I'm talking about here. Not what holds the actual O to the H. Okay? All right. Oops. So, the stronger the intermolecular force, the stronger the force between molecules, the greater the chance of this guy being a solid at room temperature. The higher the melting point, the higher the boiling point. Okay? The harder it's going to be to melt or boil these guys. All right, so that's what an intermolecular force is. Turns out there are three biggies I got to talk about. And I want you to understand. And I'll tell you right now, and I'll remind you of it again certainly before the test. You will get, on the test, a short answer question. What will one of those short answer questions be that we learned from a couple days ago? Yesterday, or day before yesterday? It'll be on what? What will it be on? Metal. What about metal? In particular, specifically, what will that question say? Yeah, it'll ask you about a property of metals. Explain in as much detail as I gave you in class what malleability is, what luster is, or what conductivity is. Okay, and that will be a long, two, 3 sentence answer because you'll have to explain the metallic bond as part of it. But the other short answer question you're going to get, and you're all going to get one of each. You're going to get one metallic property question and one intermolecular force question. It's going to be on one of these three. The first one's called dipole-dipole attractions. They're not pronounced dipole-dipole. It's dipole-dipole. These are not burets, they're burettes. And You don't use crucible thongs, you use crucible tongs. Crucible thongs would be even more uncomfortable than a regular thong. Imagine a crucible thong. You can say crucible thongs if you're with. That was funny. Not really.
Are you going to cut that out of the video?
No. That's staying there. Okay, dipole-dipole attractions. These are attractions that only occur between polar molecules. So if it's not a polar molecule, if it's a non-polar molecule, it's not going to have dipole-dipole attractions. Only polar molecules show this because what happens in a dipole-dipole attraction, it has to do with the attractive force between molecules that have some kind of difference between it. Remember my analogy of a tug of war. One guy is pulling those electrons closer to him more of the time than the other one. Well, because of that, one atom in a bond is going to be slightly more negative than the other. We've been showing that with an arrow, remember? We've shown that with an arrow. Who's pulling harder? I hope you all been doing that because I've been taking off points for it. I gave you those back, those papers, a lot of those already. Okay? So it's the attraction between oppositely charged portions of neighboring polar molecules. And look, and I'm going to illustrate it with a little picture. Like I said, these pictures are in your book if you want to look at them. I'll try to illustrate it and explain it. And then I have a little demo on it. God bless you. Okay, so let me illustrate what's going on here one more time first, and then I want to show you a little demonstration of it. In a compound like this, so I have H bound to Cl, okay? Remember, the chlorine is pulling the electrons closer to him, or at least they're spending more time around his nucleus. So it's going to have a slight negative charge here and a slight positive charge here, and I asked you to draw those on any polar molecule you saw. Same thing happens with this guy. It's the exact same molecule, slightly negative, slightly positive there. Well, the attraction between this negative and this positive is the dipole-dipole bond. That's what this guy is. The covalent bond is the bond that holds the H to the Cl. That's a covalent bond. And we know how to get those. We just look up the differences, right? 0 to 0.4, 0.4 to 1.7, 1.7 or above. This guy's non-polar covalent, polar covalent, and ionic, right? So this is one of those three. But this is going to be the intermolecular force between molecules, not within a molecule like these. Got it? Good. Let's do a little demo illustrating this point, because what I'm going to show you here, I'm going to draw. I'm sorry, I'm not going to draw. I guess I will draw up here the formulas for these guys. I've got these two burettes, which I'll show you here. These two burettes are filled with two different things. Okay? This one here is filled with hexane, and this one here is filled with water. Okay, and I'm going to use these guys in a minute. I'm going to let them empty out into the sink and show you something about them. So hexanes, which I will test second, formula is C6H14. Water's formula we know is H2O. Okay? If I asked you either of those guys, you could look them up. They could be on a test. Is this compound polar, non-polar, ionic? What would you do? What would you look up? Electronegativity difference between H and O, right? Whatever you find, that's what it is. You don't multiply it by 2. You're just talking about between one H and one O. Same thing's true here. C and H. You look up the difference between those. Turns out this guy's actually bound in a way that you actually have C bound to C's as well, 6 of them, and then you have H's all around them. But either way, the CH bond and the CC bond are both nonpolar. Both of them are below 0.4. So it turns out that this guy here is nonpolar covalent. This guy here is polar covalent. So which of those two guys can show dipole-dipole attractions? Which of those two guys has charges on them? Water. Water has a slightly charged molecule. It's not an ion. It's not like salt. You have a +1 and a -1 for sodium and chlorine. But he does have some charge to him. And I could show you the charge he has. Watch. It's kind of interesting. All I have in here, those special magical stuff, I have in these burettes, and I'm going to move my camera around to show you. I have in these burettes just plain old water in this first one we're going to test. Okay? I need this. Let's make sure I can see this from where we are. And this is the water I want to do first. And a little bit more over this way. All right, I think you can see that. If I turn the water on, you'll see it come out of the spigot. This is a called a burette, and that's called a stopcock. I know, great name. Now, watch what I do with this. I'm going to take my little furry, I don't even know what this is, some kind of fur. I'm going to rub a glass rod along it, or it's plastic or something, I don't even know. I got it from Trader. I rub this glass rod, and what I'm doing is I'm rubbing off electrons. You've all probably done this when you've touched, if I were to touch the handle now, I might get a little bit of a shock. If you've ever pushed those stupid the carts with the computers on it, you get a shock. All right, so that's like a carpet shock or a static electricity shock. So I've charged this guy up right now. Watch what happens when I put him next to water. Bet you never knew you could do this. Turn my water on, and whoop, whoop. Can you see that? Whoop. Everybody see that? What's happening? It's being attracted. The water molecules are charged. And they're charged enough to be attracted to this rod. Isn't that cool? This also explains why boys' bathrooms are dirtier than girls' bathrooms. Seriously. Okay. Doesn't it? Sure. Emily, I'll explain it later.
No, I'm not understanding. I didn't see what happened there. Like I don't.
You couldn't see that?
No.
No, I didn't see it either.
Really? Well, let's do it again. No problem there. If you guys can't see, move up. Come on up. You know, turn the light on. That will make it a lot easier. Turn the light on, too. Let's do it again. You should have said something.
Can I be in the video?
She's gonna blow her mind. Watch. Ready? Whoop.
Oh, yeah.
Can you see it now?
Oh, yeah.
You should be able to see that now.
See it? This explains why you're also blocking. You make a better door than a window. See? Isn't that cool?
See it?
I think she sees it now. I hope she sees it now. All right. Now, the thing is, when I turn this around and do the same thing with hexanes, I don't get the same result. Same basic idea. All right, but when I turn him on and I pull the little stopper off here, nothing happens. Okay? Nothing. Why? Because hexane's a nonpolar bond. I don't get any charge. Look at this. I won't even recharge it. It'll still be enough to, in case you think, well, maybe you just didn't do it right. It's like a trick. It's not a trick, see? It does it for water. It doesn't do it for hexanes. Okay? You get it, see? All right.
I kind of wanted to sit up there.
I didn't think you did. All right. So basically, all I'm showing you there, you can light off again now. All I'm showing you there is that polar bonds have dipoles in them. That's what we call dipole, two poles. Okay, one of which is going to be negative, one of which is going to be positive, and therefore, neighboring ones will be attracted to each other. These guys are going to be held together tighter than the hexane that I actually drew out of there too. Hexane is like it's similar to what you would like gasoline. Okay, it's not very far off of gasoline. When I was pouring that in, I had a stopper on top of it. I'm going to put the stopper back on because you can actually see, like you can for gasoline, you can actually see the fumes coming off as I'm pouring it because it's not held together like water is, and they tend to evaporate very easily. All right. So, matter of fact, if you were to pick up a bottle of it, this entire bottle filled with hexanes, the entire bottle filled with water, it's going to be like half the weight. It's going to be a lot lighter. Okay, it's not half, but it's going to be a lot lighter. Okay. So you got what dipole-dipole attractions are. These guys only occur with polar molecules. Now let's talk about the next kind. This is a stronger, almost like a special case for the dipole-dipole attractions. Let me move my camera back up. A special case for the dipole-dipole attractions would be hydrogen bonding. I'm talking about hydrogen bonds now, not hydrogen bombs. Those are different. I could illustrate hydrogen bonds. I don't want to be in Hiroshima or Nagasaki to illustrate a hydrogen bomb. Which I guess are the only two places they were actually used on people, right?
Hydrogen bombs?
Well, atomic bombs. Atomic bombs.
Maybe there's one bombs with water.
Okay.
Yeah, I could see that
I don't think that's what a hydrogen bomb
I'm gonna
is.
put water.
Yeah, well, atomic bombs. I meant it. The only two places, we're the only country to have used atomic weapons. That's pretty interesting. We are special. Okay, what is a hydrogen bond? It had nothing to do with hydrogen bonds. Let's talk about hydrogen bonds. What is a hydrogen bond? Well, it's a special kind of bond. It's like a special case of the dipole-dipole attractions. It's the strongest of all the intermolecular forces. The dipole-dipole kind of falls in between, because the last one I'm going to talk about in a little bit is going to be the weakest. He's the strongest, and he only occurs in very special circumstances, like if you have, well, what's one of the elements that has to be there?
Water.
No, hydrogen. It's called a hydrogen bond. Okay, water does show it, but it has to be a hydrogen bond, so it has to have hydrogen in it bound to one of three guys: fluorine, oxygen, or nitrogen. If those three guys are bound to hydrogen, you'll have hydrogen bonding. And what does that mean to the compound? Well, I'll explain. First of all, I'll try to explain to you what causes hydrogen bonding, and secondly, I'll try to illustrate for you with one demo and what you saw in the video yesterday. Talk about some of that stuff. Okay, why water in particular is so weird. That was the whole beginning of that video. I hope you watched it. I hope you paid attention, because a lot of those things that were in there relate directly to the hydrogen bond. Now, I showed that when I wasn't here, which means you probably didn't pay as good attention. In the next class, I'm going to be here when I show it to the other class tomorrow. So they will get it. So hopefully you did. All right, look at it. Here's what happens. Remember, hydrogen only has one electron. That's key. Watch. If I have hydrogen with only one electron, one proton, that's all he's got, one proton and one electron. If he is having that electron pulled away from him a lot, that's going to leave a very empty, nothing else guarding or protecting that positively charged proton left behind. Everything else after helium doesn't have this case. All right, for example, anybody else after helium has at least 2 electrons down here, and then his outer shell may have 1 or 2 or whatever. If he loses the entire outer shell, he still has some electrons guarding or protecting or absorbing some of the charge from the nucleus. That's not the case with hydrogen. So hydrogen, when he gets together with these 3 guys, who happen to be the most electronegative elements in the periodic table, right? Fluorine, oxygen, and nitrogen. You'd expect that. They're in the upper right-hand corner. They're really, really strong. When he gets together with those guys, he's almost completely stripped of his only electron. He only has one, and he's almost ripped away from it. So here he is walking around with almost a bare, naked proton. Kind of like sounds like a band. Bare naked ladies.
Oh boy, Mr. Allen.
Bare naked protons. Well, we know how seductive that can be to a neighboring electron cloud. Okay? And that's what happens. This bare naked proton, well, practically bare, it's not really, is going to be a very strong positive charge compared to, and attracted to the electrons. All right, the negative unpaired. They're not unpaired, by the way. That's the wrong word. Just called negative electrons of the fluorine, oxygen, and nitrogen. Oops. Okay. So the electrons of fluorine, oxygen, nitrogen, and they're special too because they have to be that small. They're on that first period. Okay. They have really electronegative. If you get down to the next 2 periods below, it's not as powerful a negative charge you have. The atom's not quite as small. All right, so that causes a very strong charge to be set up. Very strong attraction, I should say, to be set up. And that attraction is so strong that it gives unique properties to water and other guys who have hydrogen bonding. Okay? Okay, those unique properties include, and you saw in the video, the fact that ice floats. Water, you've already seen in labs, has a meniscus and cohesion, how water stays together in big, long streams, laminar streams. Remember those? They showed you in the video? Okay, you can't do that with most things. If I try to pour those hexanes out and use a stirring rod because it's going to help me pour it down a stirring rod, it doesn't work because it's not attracted to the stirring rod. And it's hard to pour into a nice steady stream. It's hard to pour it without spilling it, without splashing it around. But water is great for that. And of course, the big one, ice floating, I talked about this in the video yesterday. Let's face it, if ice didn't float, the world would be a lot different, like you wouldn't be here. Okay, what would happen to a pond in the winter? Yeah, it would freeze solid. As the ice, when the air temperature is below freezing, the ice would form on the top and then sink to the bottom and freeze the whole pond. But what happens is, as the ice forms, it stays on the top because it floats and protects, insulates the rest of the pond. Okay? So that's why fish can survive. As long as the water's deep enough, they can survive. As long as it doesn't freeze all the way through. Okay? All right. So, by the way, another property I want to illustrate that wasn't in the movie, I'm going to illustrate for you now in another little demonstration. Let me just make sure there's nothing else to tell you here. Yeah, well, that's just a meniscus, right? A lot of things don't have meniscuses like that. That's mercury. Mercury doesn't look like that. There's no meniscus in mercury. Okay? And let's go back to the ice one. Here's water by himself, okay? Hanging out at room temperature or whatever. Water molecules are shaped like this. They have like a V shape to them, okay? And it turns out that neighboring water molecules, as long as it's not, not too cold or too hot, can kind of get into and amongst the other one. They all kind of fit together, right? They all kind of fit together. But as you cool them down, and these guys lose energy, what starts to happen is neighboring water molecules will start to form a crystal. And that crystal, as you can see here, this is going from warmer water to cooler water to ice. The crystal has a lot of space in it. Okay? So when water freezes and those hydrogen bonds form, it actually expands because of the space. Those guys can't fit in amongst each other because they've formed these actual very strong bonds in between, forming this crystal. Okay? Now, another way I can illustrate hydrogen bonding is with a little demonstration here I want to show you. I'm going to use some water and alcohol, both of which have hydrogen bonds, but for the same thing, I could actually illustrate these guys could fit together better when you put them like this together, water with alcohol. Let me put some alcohol in.
Am I going to use not for the front?
You don't really have to for this one. You'll be able to see it. I can walk around. I'm going to add about, put that light on again for me. I'm going to add about 50 milliliters of ethanol to this guy. When I say about, I mean exactly. I'm going to try to make it exact. 50. Okay? So if you were to look at that guy, I try to make it exactly 50 milliliters. Okay? Now, I'm going to add exactly 50 milliliters of water to this other guy. Okay. We'll use the squirter to get it perfect, or at least pretty close to perfect. My eye's getting worse every year. It's harder to do this. All right. That's pretty much exactly 50 of water. Now, what's 50 plus 50?
100.
Not this time. Emily's wrong. 50 plus. Tell your math
Wow,
teachers.
that's a surprise.
I know, that does surprise me. Tell your math teachers that Emily is wrong. Because when I add the water to the alcohol, or either way, it doesn't really matter, you're going to find that when I do this and stir it up, I will get all of it out of there. I'm not going to cheat. I'm not going to trick you. I'm going to stir them up with this rod. Okay. You can see already, without me even stirring it, what do you see kind of happening here? Can you see that from where you are? See what's happening? Little tiny bubbles. And if I stir it up, you'll see even more of those. And I'm not stirring it so hard like with a blender. That I'm just stirring it, and you're seeing these bubbles rise to the top. And they're coming from the fact that the molecules are able to get in between, closer to each other because of the hydrogen bonding between the oxygen, or between the ethanol and the water. And these guys are rising. There's all that space is gotten rid of, so that when I add these guys together, I don't get 100 milliliters. 50 plus 50, in this case, when I'm all done stirring this up, is going to actually be more like about 95. Okay, see the bubbles still rising? It's almost like it's carbonated soda. Okay. And I'll do one more, and then we'll look and see what it actually reads. Okay, and it looks like it reads about 90. It's going to read about 95. So you lost 5 milliliters into nowhere. Why? Because the molecules were able to get closer together. Because of the hydrogen bond, they were pulled closer together. Space was gotten rid of. Okay, isn't that neat? All right, so hydrogen bond illustration. Turn the light off again. We've illustrated dipole-dipole attractions. The easiest one, by the way, not the easiest. The weakest one is actually this last one I'm going to talk about, called London dispersion forces. All right, a picture of some snowflakes for you. Okay, London dispersion forces. What are they? Well, these guys are the weakest, like I said. And everybody's got this. Every single compound or element has some of this force. It's the weakest thing, but it holds stuff together at least a little bit. Okay? All molecules are going to display this force because all molecules have what it takes. All it takes is protons and electrons. To be an atom or a molecule, you got to have those things. Okay, so all molecules display this force, which is caused from just one guy's nucleus being attracted to somebody else's electron cloud. Right? What actually causes this to happen is something called a momentary dipole, which I'll try to explain a little bit. But basically, here's all you really have to understand, or all you have to know for the test. It's the attractive force of one guy's nucleus for a neighboring atom's electron cloud. Thou shalt not covet thy neighbor's electron cloud. Actually, they do. And not much gets through because of his own electron cloud soaking up most of the charge. Not much is going to get through to that neighboring electron cloud. Okay, you copying that? All right, so here's what I'm talking about. Say I've got two molecules of hydrogen, right? This is a hydrogen, HH. Here's another HH over here, okay? Now, the bond between the H and the H is a non-polar covalent bond, so it's not a hydrogen bond. So it has hydrogen in it. In order to have a hydrogen bond, you have to have a hydrogen bound to a fluorine, oxygen, or nitrogen. He's not even a dipole-dipole attraction because the difference between H and H is obviously what? 0, which makes him non-polar covalent. So a non-polar covalent can only have London dispersion forces. Okay? Now, let's look at this guy. Here's the bond for this where they overlap and they share electrons. Okay? Here's the bond for the neighboring one. The attractive force I'm talking about has to be somehow due to this guy's nucleus and those electrons over here. Well, where's most of his charge going to get soaked up? By his own electrons, right? And it really wouldn't be any reason for him to be attracted to them if there was no charge, unless every now and then, remember how electrons move? They kind of move weird. At any given time, you can't really predict where they are. Well, because of that, you might, just by sheer luck, get more electrons over here on one side than on the other. It's get a very slight negative charge on one side and a very slight positive charge. It wouldn't last long, be long enough to be attracting somebody over there, maybe creating another momentary dipole in his electron cloud. And it's a very, very small, very thin, very weak charge. Okay? All right. But the more protons and electrons you have, the greater the charge is and the stronger it is. Okay? The larger the atom, the greater the attraction. The larger the atom, the greater the attraction. Okay. Let me illustrate that very easily with just a periodic table. If I have a periodic table on here, I don't know if I do or not. I don't think I do. No. Well, I'll just use one over here. This won't be on the video. Let me just use this over here. Just take a look over at the periodic table over here. Okay, watch. I can illustrate this by the period 7, or I'm sorry, group 7. Fluorine, chlorine, bromine, and iodine. Remember those guys? They're part of the ones that we call diatomic elements. Diatomic elements are the ones that form a bond with itself. Every one of those, F2, Cl2, Br2, and I2, listen up here, look here. Okay, every one of those guys is form a bond with only himself. What must that bond be? Polar, nonpolar, ionic? Nonpolar. No charge, right? So the only kind of force between these guys would be the London dispersion force between them all. Fluorine, chlorine, bromine, and iodine would only have London dispersion forces. Look what happens as they get bigger, and you get more protons and more electrons. Fluorine and chlorine are both green. What does that mean they are on this periodic table? What does green mean? Do you ever figure that out? They're gases. They're gases. Everybody who is up here green is a gas. The pink ones, there's only one other one, it's not on that because it gets cut off, that's mercury, are what? Liquids. And the yellow ones are solids. So look what happens as you go down. As they get heavier and you get more and more protons and electrons, you get stronger force, stronger intermolecular force, enough to make, enough of that, the London dispersion forces to actually make iodine a solid. It's not very held together very well. It's kind of weak. I'm going to show you a demo on that when we talk about sublimation as well. Okay, so a little summary here before I finish up. You need to understand when I say strong and weak, they're all relative terms when it comes to intermolecular forces. Because look at the amount of energy it takes to break an ionic bond. 500, depending on the bond, 500 to 5,000 kilojoules of energy per mole. Here, for a covalent bond, 100 to 1,000 kilojoules of energy per mole. The strongest of the intermolecular forces, hydrogen bonding, only takes between 10 and 40. And he's the strong one. The weaker ones, dipole-dipole and London dispersion, is 5 to 20 or 1 to 10 kilojoules per mole. They're much, much, much weaker. Even the strongest of these doesn't compare to a real covalent bond or a real ionic bond. Okay? These are the bonds between molecules. See? HX, HX, between. That's the bond I'm talking about. The bond that holds the molecule together. That is the covalent bond or the ionic bond. Okay? All right, good enough. Now,